Hi there. This video is going to introduce you to the favorite unit of all chemists everywhere, which is the mole. Okay. Um, in reality, okay, we rarely deal with chemical reactions that happen with just one or two molecules. Okay, so we've introduced the idea of atoms and molecules and chemical formulas that tell us how many atoms are in our molecule. Okay, but usually when we're dealing with things on a laboratory scale or on a global scale, okay, we're dealing with tons and tons of molecules. Okay, in fact, if you just consider a cup of water, there's about 10 to the 24 molecules of water. Okay, so that's a lot of zeros, okay, after that one. A lot of molecules. Okay, so just imagine doing calculations or writing reactions, equations that account for that many molecules all the time. Okay, it gets overwhelming. We don't want to deal with numbers like that. Instead, chemists have developed a more convenient unit that we use so we don't have to deal with those large unwieldy numbers. Okay, and that unit of convenience is the mole. Okay, 1 mole is defined as 6.022 times 10 to the 23rd molecules or atoms or any entity that you're interested in. Okay, and that's also known as Avogadro's number. So if you ever see Avogadro's number referenced, that's this number. Okay, so you will eventually remember this number off the top of your head because you're going to use it so much. Okay, but for now, just keep this handy for any calculations that you're going to be doing with mole. Turns out that this number comes from a pretty simple definition. Okay, it is the amount of any substance containing the same number of entities as 12 grams of pure carbon 12. So carbon 12 is our kind of reference point for defining our mole. Okay, it's pretty arbitrary. We could have picked any element. Just turns out that carbon was the lucky winner for us. Okay, so this is going to correspond to the number of atoms, number of molecules, number of photons. You could calculate the number of professors in a mole. Okay, it really doesn't matter what kind of quantity you're dealing with. Okay, everything can be put into the unit of a mole. Important thing to remember is that the mole represents a quantity. Okay, so here we're talking about a quantity, the number. It represents a number of objects. Okay, so now that we've introduced the mole, we can now describe our masses of atoms and molecules in terms of molar mass. Okay, so just yet another way to describe the mass of whatever we're dealing with. Okay, so conveniently, it is the same units, sorry, it's the same magnitude as the molecular and formula masses we've already introduced. Okay, remember those were in units of AMUs or atomic mass units. Okay, so very tiny. Remember those masses were talking about one atom or one molecule. Okay, very, very tiny, tiny amounts. Okay, so these are tiny. Okay, when we talk about things on the molar scale, then we're talking about more macroscopic or large quantities, quantities that we're dealing with in our everyday experiences and environment. Okay, so that's a much larger quantity. So large. Okay, so again, conveniently, they're all going to be the same numbers. Okay, we're just dealing with different units. Okay, so if we take carbon as an example, okay, if we want the mass of one atom of carbon, okay, the average atomic mass of that is going to be, again, you just grab that off of the periodic table, that's 12.01 AMUs. Okay, if we want the mass of 1 mole of carbon, again, that's a much larger scale, right? Lots of atoms, we just said, in a mole of carbon. Okay, we grab that number still off of the periodic table, so it's still 12.01, okay, except now we give it the units of grams per mole. Okay, so there's 12.01 grams in 1 mole of carbon. Okay, and then if we wanted to figure out how many atoms were in that mole of carbon, okay, that's where Avogadro's number comes in. So there are 6.022 times 10 to the 23rd. A lot. It's a lot of zeros there. Okay, 6.022 times 10 to the 23rd atoms in 1 mole of carbon. Okay, so, oops, my units are offset here. But anyway, so hopefully that just reminds you that you're still dealing with the same number that you're reading off the periodic table. Okay, so that 12.01. Okay, if you're talking about an individual atom, okay, then you want to be in units of AMUs. If you're talking about the larger quantity of a mole, okay, lots of atoms in that case, then you're going to be in units of grams per mole. We are going to use the unit of moles and molar mass forever now. Okay, you've now entered the world where you're going to be thinking in terms of moles a lot. Okay, so now we can know the number of atoms and molecules in a sample. Okay, a sample of whatever you're interested in. And that's going to become really important as we start talking about chemical reactions and all the fun stuff down the road. Okay, so right now just developing that familiarity and that skill with thinking about quantities of our chemicals, of our molecules, of our atoms in terms of a more meaningful number when we're dealing with the large scale of those things with our new unit of the mole. And one last thing that I will note here is that our chemical formula, as well as telling us how many atoms of each type we have in our molecule, it also represents how many moles of each atom we have in our molecule. So we could say, let's go back to our example of CO2. Okay, so remember before, when we were talking about our chemical formulas, we said that this formula tells us that we have 1 carbon atom and 2 oxygen atoms in 1 molecule of CO2. Okay, well, this formula also tells us that we have 1 mole of carbon and 2 moles of oxygen for every molecule of CO2. Okay, so we can also use those chemical formulas to give us information about the kind of molar makeup, the larger scale makeup of our compounds. And we'll see that that will come in really handy again when we start talking about chemical reactions. Okay, so just keep that in mind for down the road. So chemical formula tells you not only number of atoms, number and types of atoms that are in your compound, but also the number of moles of each element in your compound. Okay, so you might be asking yourself, well, the mole is a new measure of quantity of how much of something I have. Okay, can I just go into the lab and measure out how many moles of carbon I have? Is there a mole balance that we can use in the lab? That would be really cool, but unfortunately we do not have such a device. Currently we can only measure in grams, okay, or pounds, or whatever unit your scale reads out to you. In the lab, that's usually going to be grams for us, okay? But don't fret, because we have the power to convert between moles and grams and atoms, okay? So with all of the new tools that we've developed, we can go from one of these quantities to the other pretty easily, just doing the same kind of unit conversion that we've already been practicing. Okay, so here is how all of these things are related to one another. Okay, so we can directly convert from mass, which is in grams, to moles. Okay, and the way that we do that is to simply divide by your molar mass. Okay, so remember, this is information that is readily available to you just by having a periodic table handy. Okay, so remind yourself, just keep that periodic table handy and you can do that conversion. Okay, and we also have the power to go from moles. This is the OSO shortened abbreviation for mole that you'll become familiar with. Okay, we can go from moles to atoms or molecules. Okay, remember we do that using our Avogadro's number. So in this case, we would multiply by Avogadro's number. Okay, so remember that's 6.022 times 10 to the 23rd. Atoms, etc. per mole. Okay, so essentially what we've done here is just introduced another type of unit conversion for you to use just like you've been using in our other dimensional analysis examples. Okay, so just like converting between centimeters and meters, okay, or grams and kilograms, we can convert between mass or grams, moles, and atoms or molecules. Okay, so you have all of those conversion factors. You're just going to be doing the same thing as you normally do with dimensional analysis, and that is to use your units. Okay, always include your units, and you should be able to get yourself where you need to go. Okay, so let's practice some of those conversions. Let's put our new tools to work. Okay, so let's look at this first example. We want to know how many moles are in 10 to the 3 grams of H2O or water. Okay, so that's approximately the amount of water in one of those big 1 liter water bottles that you drink every day. Hopefully you're drinking your water. All right, so where do we want to start? Okay, so always start with what you know. So we know that we have 10 to the 3 grams of water. So we can also write that as 1,000 grams. Okay. So where can we go from here? We want to get from mass to moles. Okay, so can we go directly from grams to moles? Do you have a unit conversion that allows you to do that? In fact, I think we do. And it's called your molar mass. Okay, so remember, start with your units. We want to go from grams to moles. Okay, now ask yourself, do I have that conversion factor between grams and moles? Do I have something with a unit of moles per gram or gram per mole that I can plug in here? And in fact, we do have our grams per mole. So remember, if we go back here, right, that's going to be our molar mass, right? Molar mass has units of grams per mole. Okay, so we have an easy conversion factor there. So go grab your periodic table and figure out how many grams are in 1 mole of water, right? So we've got 2 hydrogens and 1 oxygen. So add those up, figure out your molar mass, and plug it in. And once you do that, hopefully you find that you have, I'm just going to round now. I know we did a lot of exact calculations before, but we'll keep it simple on these examples and just do some rounding. So you should get about 18 grams in 1 mole for your molar mass of water. Okay, and then if we punch that into your calculator, you'll end up with, hopefully, 55.5 moles of water. Okay, don't forget to put units on your answers. You always want to know what your number means when you're finished. Okay, so why don't you pause the video, take a few minutes to work through the other 2 examples and see how you do. Don't forget all of your conversions, your conversion tricks that we've just introduced. Okay, so remember you have the tricks of your molar mass, so grams per mole, okay, as a conversion factor. And we also have Avogadro's number, so atoms or molecules per mole there. Okay, so take a few minutes and try your hand at at examples 2 and 3, and then you can check back here and see how you did. Okay, so hopefully you've had a chance to try number 2. Okay, so this is just essentially the opposite direction that we did in number 1. So instead of going from grams to moles, we're going from moles to grams. Okay, so start with what you know. We have 0.135 moles of NaCl. We want to get to grams, and we have that conversion factor of our molar mass again. Okay, so we want moles to cancel. Okay, and then grams up top. That tells us the way that we want to do this conversion factor. So we want the actual molar mass, grams per mole, and there are 58.44 grams in 1 mole of sodium chloride. Okay, so again, just adding up the mass of sodium and the mass of chlorine from your periodic table, you should get 58.44. Punch that into your calculator, and we're ending up with 7.89 grams of sodium chloride. All right, so for this last one, I'm going to work through it stepwise just to show you how I approach these types of problems. So this one's going to be a multi-step conversion. Okay, so we're going from grams of oxygen and we want to get to molecules. Okay, there's no direct relationship between those two. We need to do an intermediate step where we get to moles first. Okay, so moles is our magic converter here. Okay, and I just want to show you how I tend to approach these kinds of multi-step dimensional analysis problems, okay, where I really focus on the units and let the units direct how I do my calculation. Okay, so as usual, I'm going to start with what I know, which is that I have 85 grams of oxygen. Okay, so I know that I have grams and I want to get to molecules. Okay, so how are we going to get there? Well, I know I want to get rid of grams, so I'm going to put that on the bottom. Okay, now I think about what kind of unit conversions I have available to me. Okay, I don't have anything, like we said, that goes directly from grams to molecules, right? There's nothing that allows us to do that direct conversion. Okay, but what I do have is the ability to go from grams to moles and then moles to molecules. Okay, so let's start with our first unit converter, which is going to be our molar mass. So I can go from grams to moles. Okay, that cancels my grams. Now I'm in units of moles. Okay, so we've essentially just done what we did up here in part 1. Okay, but we're going to keep going because we want molecules, not moles. Okay, so one more step. Okay, so I want to go from moles to molecules. Do I have a conversion factor that allows me to do that? Yes, we do, right? That's our Avogadro's number, right? So remember, Avogadro's number tells you how many molecules per mole that you have. So these units right here, so molecules per mole, that is essentially your unit for Avogadro's number. Okay, so then that means my moles cancel, and I end up with the unit that I'm looking for. Okay, so this is how I set up all of my calculations, all of my dimensional analysis calculations. I do the units first, make sure those work out, make sure I have them in the right order, that I haven't flipped anything. Okay, make sure things are canceling out correctly. And then I put the numbers in that correspond to those conversions. Okay, so numbers that are going in here. So I need a molar mass for oxygen. Okay, so be careful here. What do we know about oxygen? Okay, oxygen, remember, is one of those diatomics that we mentioned. Okay, so make a list of all of your diatomic gases. Okay, make sure that you don't, by accident, just do an atomic oxygen. Okay, so we want molecular oxygen here. This is the stuff that you're breathing, O2. Okay, so this is O2. So we have 2 atoms of oxygen in every molecule. So that means we have about 32 grams per mole. So we're going to put 32 in the grams per 1 mole. Okay, again, just grabbing that off of your periodic table. That's your molar mass for oxygen. And then we need the conversion for molecules to moles. Okay, so that's our Avogadro's number. So remember, it's 6.022 times 10 to the 23rd molecules in 1 mole. Okay, so that's 6.022 times 10 to the 23rd is going to go up top. So we have a lot of molecules, didn't mean to erase, in 1 mole. Okay, so again, this is where we want to think about, does my answer make sense? Does my process make sense? Okay, take the time to ask yourself that question. I can't tell you how many times I see this ratio inverted or this ratio inverted. Okay, so make sure your units are canceling the way you want them to. Make sure you have your number in the right spot, right? It's not 32 moles in a gram, it's 32 grams per 1 mole, or 6.022 times 10 to the 23rd molecules or atoms in 1 mole. Okay, so just those are where I see the most mistakes, so just be careful on that. Okay, so take a second and punch that into your calculator. And once you do that, hopefully you end up with a number that looks like this, 1.60 times 10 to the 24, or something very close to that. Okay, so remember to put your units on there. We ended up with molecules, so that tells us that we have 1.6 times 10 to the 24 molecules of oxygen in 85 grams of oxygen. Okay, now again, last step, does my answer make sense? Okay, does it make sense that we have a ginormous number of molecules in 85 grams of oxygen? So 85 grams, you could hold that and it would feel, you would feel that mass, it would feel pretty heavy, okay? So it makes sense that there's a lot of molecules in there. Now, if you had by accident maybe inverted this ratio, okay, you would have ended up with a really tiny number in your exponent. Okay, so when you ask yourself, okay, does it make sense that I have a really small number, like fractions of molecules in a mass of oxygen that I could actually feel the weight of if I held it? That answer hopefully would be no, that does not make sense. Okay, so again, just asking yourself that question at the end helps you catch some simple mistakes in your calculation. So don't skip that part. Okay, well, hopefully this helps to help you feel comfortable doing these conversions with grams and moles and molecules, okay, putting our molar mass into use and our Avogadro's number into use. Okay, so this is a really powerful skill to develop. You're going to use this throughout the rest of your chemistry career. So it's really important that you feel comfortable doing these types of conversions. They're not going to go away, and they're going to be so helpful in helping you to get some really interesting information as we go along in the course. Okay, so keep practicing those, and don't worry, you'll get lots and lots of more practice on these as we go along. All right, hope that helps. Thanks.